Hey guys, this is Steven from the Legit Tech Tutorials, and I wanted to continue talking about the Dyno project. I made a lot of mistakes in the last video. Number one was that here this is r squared, here a squared plus b squared, and then this is r squared, not d squared. So I got mixed up by this guy because this guy's asking for diameter and this guy's asking for inches. So what I'm thinking about doing is kind of making this to do some calculations first. So I told you kind of what we have at the shop. We have at the steel store we have an 8-inch ID by 8 and 5/8 OD piece of steel. So what we're gonna do is we're gonna jump into Swift Calcs. I'm sure you guys have seen that in multiple places. Let's go into Legit Tech Tutorials. Okay, so this is, I've never used it before, it looks like, using Legit Tech Tutorials. Okay, so this is Swift Calcs, and you just log in using your Google, and then what happens is all of your stuff is public, and it's basically free to use, but you only have so many sheets, and everything that you do is public. Create additional worksheets. Oh, name on your new project. This is Dyno. What the heck? It won't let you create any now? Oh. Holy shit. Oh, this is everybody's. I see. Huh. Well. And they want a lot of money for this thing too. Actually, hobbies not commercial. $25 a month, that's a lot. Well, then that means I kind of don't really want to use it. So this is what we're going to do. I really like that program. I really want to use it. Very strange. So what can I do? I can only mess with other people's stuff? Okay. Anyways, I really want to do it because it keeps all our units. So what I'll do is I'll test everything in this and then transfer it over to Google Sheets, which is basically what is it called? Excel, pretty much. So let's pick a different one that I already have worksheets on. For whatever reason, these guys are not letting you create new worksheets. Yeah, sure. Okay, so this one I'm gonna call, oopsies. This one I'm gonna call Dyno. Actually, let's change this to log out, and let's go into the car one. I don't know if I've used it on that yet. Let me see. Okay. Oh, there it goes. Strange. Wouldn't let me do it in the other one, but it would let me do it in this one. I think what it did... Oh, because I think it's like a business trial is currently active and expires in 9 days. Okay, so basically it looks like I have 9 days to do this, which is not going to be very long with this project. But let's do it here anyways, because you see it says business here. So basically it activated a trial for me. Okay, so I'll show you guys how to use the software, and then I guess you can think about whether you think it's worth it or not. Okay, so let's put this guy here. So Dyno. Okay, so Dyno, and we have here, we have moment of inertia of this one, and then cylinder, solid cylinder. So what we need to do is we need to look at this. So let's say density A36, and I think there's a lookup table. Data. Material library. Steel. Iron alloy. Technically it's iron alloy, carbon steel, 836. 836. Select material. Okay, so now basically what I could do is go here and say A36. So I'm going to say dense equals A36 dot density. I think there's a function, something, I can't remember, A30 or A36 dot, oh, there it is. So this is dense equals there it is. Density, and there you go, 7.9 kilograms per meter cubed. So then we want to do volume, so we're going to say O, and then this is where I can show you here what we use if you're not familiar with this software. So we could use two sliders and call this IDOD. Sorry, I'm checking all my emails because people are emailing me because, oh, that was from SwiftCalcs, because today is my today's October 1st, and I was born October 1st, 1993, so today is my birthday. Okay. 0.1, and this is, let's say, 30, and step size is 0.1 inch. Same thing here. 0.1, 30, step size 0.1 inch. And I'll show you guys how to do more stuff with that. So now I could select in here, and we're about 11, and so that's 8.6 OD. There we go. ID is 8 inches. This tab, there we go. Okay, and then basically we want to, oh, and then we need one more, which is length. This is also in inches. And also this is going to be maximum 30 and 0.1 and 0.1. And right now I'm thinking maybe 24 inches or 20 inches. Let's say 20 inches. Okay, so mass equals dense times OD times ID times length. Oops. And this is some sort of typecast thing, kind of interesting. I've never done that. And then if you type it in again, it'll tell you what that number is. And it says 84 kilograms, and then we convert that to pound mass. Wait, pound force. Pound mass. Why is it doing that? Strange. Okay. So as you see here, we kind of convert the units. We could change it to approximate, or we could have it exact. Generally exact will do some sort of give you some equation, right? Okay, so that is our mass. It's about 350 pounds. And you can type it in again, and if we type it in again, we can change this units to pound. There we go. Pound. Okay, and so now about 400 pounds, which is not light. And we might have 2 of those. So mass. So there's going to be 2 rollers, right? There's a forward and backward one. So let's look at it kind of an example here. So this is Dyno. These are, they used to be mainly inertia, but now they're inertia eddy current, basically. Eddy current. I think this one might be just inertia. This one I think is just inertia. But look here, drum diameter 24 inches. Drum width 81 inches, maximum axle weight 3,000 pounds. Timing accuracy plus minus 1 microsecond. Drum speed accuracy plus or minus 1/100th of a mile per hour, 1/10th of an RPM. So that gives you an idea. They're talking about, they're 24 inch, so they're about 3 times the size as our drum, right? And the width is 81 inches, which is about 4 times the size of ours. So, but if you could see here, it's only single drum, right? Not dual drum. Dual drum, I think, is a little bit more stable. Single drum, you have to kind of fasten the car down a little better, quite a bit actually. So you have to fasten that car down quite a bit in order to get it to stay on top of that drum. But what I'm thinking is that I think that this here might be a little bit too heavy. So let's drop this down. So we need at least, so let's see. So here we go. So what does the number on the tire mean? So you have P225, 45, R17. 17 is the rim size. The 225 is the width, right? Okay, here. In the example above, the tire's width measured from the widest point of the inner sidewall to the widest point of the outer sidewall when properly mounted is 225 millimeters. So, oopsies. If you see this, see here it says 225, 45, R17. 225 is the width of the tire in millimeters. So, millimeters to inches. So let's say we want to do a 300 millimeter tire. That's so my neighbor has a 295. My car has my Mustang has 235s, and my Rabbit has like 205s or something. So I'm gonna say like 15 inches is probably the smallest I could go. I mean, obviously the smallest I would go is like 12, but let's say right now 15 inches. So we could maybe do one drum, because here is 300, so you're talking 600 pounds each, and there's two sets, right? So there's one for the left tire, one for the right tire, so they're two separate pieces. So it might be interesting to put it all on one drum, but that's a very getting it to line up perfectly on the drum and not move, because one drum I feel is very dangerous as far as moving. I'll have to look more at it and see if that is indeed the case, because it does look like that way. You can see here this guy's got 2,000 horsepower possible. Okay, so yeah. So this is kind of an example, and you can see here that this drum probably weighs quite a bit. Anyways, so, and here down here it says a forklift. Usually it says forklift. 5,000 pounds. 5,000 pound forklift. Okay, so now whether or not it weighs 5,000 pounds is another story. Okay, so we have the mass. Now we need to do moment of inertia. So moment of inertia. Moment equals 0.5 times mass times, and this is really cool where it does the abbreviation. So A squared is the radius from the inside to the outside. So basically we got to take the OD and divide it by 2, and then squared plus ID over 2 squared, and moment. If this is in kilograms, we want it in inch pound times inch squared. Inch pounds. Okay. So that is our inch pounds, 5,000 inch pounds. So now what we need to do is we have that moment. So now we have moment dual roller moment equals moment times 2 dual roller moment. This again, change units, inch pound, not pound force, inch pound. There. Okay. So dual roller moment inch pound. Okay, so now what we need to find out, ID divided by 2. Right, that's correct. Okay, so what that means now is now we need to find out how much force is required. So let's look at Okay. So here's kind of an idea. This is more of like a rolling example, but it will also help us. So basically here, a rolling object accelerating down an incline. So force net is power in some vector over time, right? So force is force equals ma, right? Which is acceleration is basically velocity over time, right? And so this is like the change of, it looks like point mass. We have, oh, this is a point mass. But a point mass is basically an infinitesimally small, like a molecule or like an atom. So like as small as you could think, it's just a point. It's so small it doesn't have any volume, pretty much. So here is kind of the thing that we're looking at. Torque net is I a vector, I acceleration. Torque and angular momentum are actually pretty complicated. Okay. So that's basically of I half mr squared is of a cylinder. So here he's doing kinetic energy, torque, kinetic rotation, and potential energy. So here is kinetic energy, here's the rotational energy, and here is moment. So basically what he's going to do, he's going to move this over to this side. So 1/2 mv squared 2 plus 1/2 I moment of inertia, angular velocity squared. So this is mass and this is velocity. So this is like, this is basically kinetic energy. This is kinetic energy plus this is equal to this. So basically it's turning the energy of potential energy of it going down into kinetic energy, but it's not exactly perfectly going down. There's an angle to it here, so it's actually at an angle there. So here he's going to go into, eventually he's going to go into the angle here. Anyways, yeah, so here's velocity, etc. So basically we're going to use this equation here. So pretty much what we're looking at is we want to know angular acceleration. So not linear acceleration, but angular acceleration, right? So how fast is this wheel spinning or changing rotational speed, rads per second, right? Which is angular acceleration. Rads are degrees, or however you want to think about it. Rads are basically pi is half rotation. 2 pi is full rotation. So rad is 360 degrees is equal to 2 pi, which is 6.28 whatever after that. Right? So here you see this is the alpha sign, lowercase alpha. Yeah, so that's in rads per second. So that is the equation that we are going to use there. So let's go ahead and look at that. So what I found is that an average dyno run is anywhere between 7 to 10 seconds. I saw a Mustang do 10 seconds. I saw a Rabbit with a souped up motor, and the Mustang was stock. I saw a Rabbit with a souped up motor be on there for 7 seconds, and the Mustang be on there for 10 seconds. So somewhere in between there is the time that we need to accelerate it up to max speed, let's say. So let's do some things here. So let's say max drum RPM. And then this is going to be in 1,000 probably. 1,000 steps. 1,000 increment. And maximum is, let's say, 20,000. Minimum is 1,000. step is 1,000, and then this is RPM, revolutions per minute. Okay, so let's say that it is, so this is another thing, because if you think about it, the roller is 8.5 inches in diameter, but the wheel is way bigger. So inside the car, let's say that it says that your car is traveling at 140 miles per hour. That's actually the circumference of the wheel. Now, if you compare the circumference of that wheel compared to this drum, it's going to be spinning way faster. So that all depends on the size of the rim, right, and the size of the drum. So we also need to do that here to make sure that we don't over RPM the drum. And the RPM of the drum is going to be determined by the bearings that we find that are going to run inside the drum. So max drum RPM equals blah blah blah, whatever. 15,000 RPM, let's say. And then let's say we have another one, dyno time, or let's say horsepower. Wait, what? Let's just call it HP max. In this case, it's basically the car, pretty much. Let's do it in one step. Let's do it 300 horsepower. Okay. So let's say I'm running my Rabbit. My Rabbit stock is 53 horsepower. Let's say. Okay. So max dyno RPM. I don't think we need that right now, but that's yeah. So what we need to do is we have the moment, and we need to find the torque at a specific RPM. So let's say max. So let's say here measured RPM. Let's just say measured RPM. So this is basically where we are measuring. And let's say that this is the engine RPM in actuality. So this is a maximum of, for a car. I'm thinking that these could also be used for a motorcycle as well. But for a car, let's say this is 100, and let's measure it every 100. So I'm going to say that this is like 7,000 RPM, let's say. I'm sorry. The Rabbit, I think, is like 51 something. So 5,000 RPM max horsepower. So at this point, what is our acceleration? So IA, angular acceleration, is equal to T minus W. Let's see. Yeah, so rads per second per second. Classical mechanics, force equals mass times acceleration. So basically, yeah, so A is equal to change of the angular velocity over time. So basically, the orbital angular acceleration of a point particle alpha can be connected to the applied torque T by the following equation, where I is its moment of inertia over time. So obviously our moment of inertia is not changing over time, so we don't have to do math with that. So this is like the change of moment of inertia over an infinitesimally small amount of time, but our moment of inertia does not change over time. So it's torque minus angular acceleration, pretty much, angular velocity. So IA so from this we could determine torque, and then we could determine the speed of the rotating drum, and from that we can interpolate from torque back to RPM, because again horsepower is basically torque times RPM, and then it will do the solution. It will convert the units for us, SwiftCalcs. So IA equals torque minus IW, right? So we want torque, but we need to know angular acceleration. So we already have torque because we have horsepower, right? So torque is known. Torque is known, check. Why did I say I twice? Minus di. Okay, so let's move those two over. I believe that's di. Distance, origin. Yeah, with the constant of proportionality being the moment of inertia of the particle. So basically, we're going to move I and we're going to move IW over to the other side. So now it's plus IW, and we're going to separate I out, and then it's I alpha plus omega is equal to torque, right? Okay, so we have torque, we have angular momentum, we have I, so then we'll know angular acceleration. But in this case, we want to find out torque. So, because we're going to measure, we're measuring the angle. But the question is in this calculator, what are we trying to measure, pretty much? So we are trying to measure torque. We are trying to calculate torque, which is then going to give us horsepower. If we can read the engine RPM and we have torque, we could get horsepower. So what we actually have a probe on is alpha, which is the angular acceleration, which is this bad boy right here. So basically what I want to determine is at this specific, because I want to do a couple things with this calculator. Number one, so I want to do a couple things. Number one, I want to make sure that it doesn't over rev whatever bearing we put on there. So that's number one. Number two, is it going to slip? So if we go online and we look at the rubber friction coefficient to steel, and we look at the specific amount of power, let's say the Mustang, let's say 250 horsepower or whatever, is it going to slip on both of these rollers? And another thing is, what is the max horsepower that we can put? So here's the question: what is the max horsepower that we can put down that will cause it to not slip, right? So I think that is the equation that we are looking for. So if we have these two drums and we have the weight of this car, what is the max horsepower that we can dump into this thing without it slipping? Okay, so let's do a couple more things here. So friction. Friction coefficient of multiple materials, so we're looking for rubber. Surface conditions. Okay. Horseshoe, what? Okay. Oops. Rubber on rubber, rubber on dry asphalt, wet concrete. Huh. So it has it on asphalt, but not steel. So rubber and steel coefficient of friction. Oh, this is some paper. Okay, here we go. Greasy aluminum, rubber. Let's see. Rubber. Greasy aluminum, greasy rubber, dry rubber. Dry rubber, dry steel. Here we go. So, we're going to use this as an estimate here. And what I think I'm gonna do right now, we're at 35 minutes, so I'm gonna just continue this video right after I talk to my buddy here. Again, he's messaging me because of my birthday. So I will upload this, and within the 6 minutes, I'll probably be back to continue this thought, as I'm pretty close to getting sick. So I want to kind of get some of these videos out before that happens. So I can have some footage for you guys already ready to go. So I'm going to go ahead and do that, and I will see you guys in a little bit.